In this section, we are going to use Riemann sums to find the exact area under a curve. And we're going to do that using sigma notation. And we're going to find out that we can express certain Riemann sums in terms of n, where n equals the number of rectangles. And then we're going to be able to allow n to go to infinity, and then in taking that limit, we'll actually find the exact area under a curve. So this is a really neat section. This is pretty cool. It's a complicated process, but I find that it's the sort of process that students like to do. You know, it gives you something to do. You know what you're doing. You understand what you're doing. You just got to be meticulous and do it right, and do all the algebra right, and get the right answer. And so when you work through these, it actually feels really good. It's kind of like a puzzle, and it gives you a sense of accomplishment. And so this is really a fun section. And so we're going to build up to this, and I'm going to start by introducing sigma notation, which very likely you've maybe seen in some other classes, I don't know. And then we're going to talk about how to manipulate it and simplify expressions involving the sigma notation. Then we'll learn some formulas that we'll need for finding sums, certain sums, and then we're going to pull it all together at the end and use the limit of a Riemann sum to find the exact area under a curve. So here we go. So basically, this is sigma notation. This is it looks like, to me, it looks like an E, but it's a capital S in the Greek alphabet. And so this is like taking the sum as k goes from 1 to n. That's what these refer to. And then this a of k is some formula that involves k, and that formula is kind of the formula that gives you each term in terms of k. And so when you do it from k equals 1 to n, you're taking term 1, 2, 3 on up to n, and then you're adding all those together, and that's what this sum expresses. So I think the best thing to do is just show you some examples here. So this is the sum as k goes from 1 to 5 of the expression 2k minus 1. So the idea is, for each of these terms, we're going to plug k into here, starting with 1. So the first term would be 2 times 1, and you know, I probably don't need that parentheses. 2 times 1 minus 1. Okay, that's like the first term. And then we're going to add, well, yeah, the parentheses is good. Then I'm going to do for k equals 2. So 2 times 2 minus 1. And then for k equals 3, so 2 times 3 minus 1. K equals 4, so 2 times 4 minus 1. And then k equals 5, 2 times 5 minus 1. Okay, so you may have noticed here, this is 2 minus 1, which is just 1. This is 4 minus 1, which is 3. This is 6 minus 1, which is 5. And this is 8 minus 1 is 7. And then 10 minus 1 is 9. So you find out that this sum is really a way of expressing the sum of the first 5 odd numbers. And this would be like 10, 20, 25. And I get the sum there. Okay, so oftentimes these are expressing something, a certain sum, and this was the sum of the first 5 odd numbers. This is like an expression for an odd number, and then for each value of k you get the next odd number. So what about this here? Okay, well, the first one I'm going to put in, this is from 1 to 3, so this would, putting in k equals 1 in for k, so this would be 1 plus 1. This would be 1 over 2 plus 1. That's 2 for k. Oops, sorry, this is plus. And then putting in 3 for k, 1 over 3 plus 1. Okay, so we're putting in k equals 1, 2, and 3 into this and getting these three terms. So this is really 1/2 plus 1/3 plus 1/4. And then we could actually find this. We'd need a common denominator of 12. So this would be 6 12s plus 4 12s plus 3 12s. And this is like 13 12s. That's what this would be. So that's what this sum represents. Okay? So it's like a half, a third, a fourth, and if you had this number was higher, it'd be a fifth, a sixth, a seventh, so on. And then you're adding them all together. Okay, so what about this one? This kind of illustrates that you don't always have to start with k equals 1. K could start with anything, just like it can end with anything. So the k is going from 5 to 9, and the expression is k squared. So this would be like 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared. And this would be 25 plus 36 plus 49 plus 64 plus 81. It's the sum of these 5 square numbers from 5 to 9. And then, I don't know how well you can see this, but I'm going to have to use this 85 because I can't find my charger. I might have left it at work, but the battery is low on my other calculator. So I don't know how well you can see this, but I'm just adding these up. So 25 plus 36 plus 49 plus 64 plus 81. And it looks like I get 255 for that sum. Okay, so that gives you kind of a basic introduction to how this summation notation works. Okay, so now what I want to do is I want to illustrate here that there's more than one way to express the same sum. For example, the sum of the first odd numbers was given by this sum. This is what we used before, and we put in 1 to 5 into here, and I got 1 plus 3 plus 1 plus 3 plus 5 plus 7 plus 9, and that ended up being 25. Okay, so that was a way of expressing the sum of the first 5 odd numbers. But there are other ways of expressing them. In particular, let's say I go from 0 to 4. Instead of 1 to 5, I go from 0 to 4. Then I could change this expression here somehow. So how would I need to change this? If I put in 0 here, I would actually get -1, right? But let's say I do 2k, instead of -1, I do +1. Then when I put in 0, I would get 0 plus 1, and that would give me 1. So it'd be like 2 times 0 plus 1. And then 2 times 1 plus 1. And then 2 times 2 plus 1. And then 2 times 3 plus 1. And then 2 times 4 plus 1. And then you see here, this would give me 1. This would be 2 plus 1 is 3. And 4 plus 1 is 5. And 6 plus 1 is 7. And then 8 plus 1 is 9. So it's just another way of expressing the sum of the first odd numbers here. It would give you the same value. And there's really just kind of an infinite number of ways. Let's try another one. Let's say I do k equals, we'll say 5 to 10. That's what I think that would be. And so what would I need to do? Well, I would want to get 1 to begin with. If I put in 5, I would get 10. right? And then I think I have to subtract 9. That would give me 1. So let's see if this would work. So if I do 2 times 5 minus 9, and then I would get plus 2 times 6, that'd be 12, minus 9, that would give you 3, and then 2 times 7, that'd give you 14, minus 9 is 5, and I'll continue down here. 2 times 8 would give you 16, minus 9 is 7, and then 2 times 9 would give you 18 minus 9 is 9. Okay, and that would give me 1. So notice I got that wrong. It's not 5 to 4, it's really 5 to 9. And that gives you 5 terms. It's because it includes the 5 and then 6, 7, 8, 9. Okay, 0 to 4. If you notice, if I subtract these, I get 4. 5 minus 1 is 4. 4 minus 0 is 4. 9 minus 5 is 4. So when you subtract those, you don't get the number of terms, you get one less than the number of terms, because the terms include the 5 and goes up to the 9. Okay, so this would be 1 plus 3 plus 5 plus 7 plus 9, and that's equal to 25. So the point here is there's many ways of expressing the same sum. Okay, and in fact I think there's an infinite number of ways, because you can always change these and then adjust the formula. It's really similar to like a horizontal shift in a graph. You're kind of doing, by shifting these, you're kind of changing the k before it goes into the formula. So it's kind of has that counterintuitive, you know, daylight savings time. When you set your clock back, you gain an hour of sleep sort of thing. Okay, so here I set it back and I gained an hour. Here I moved it forward from 1 to 5, 4, so I gained, you know. So, okay, very good. Good enough. That's good enough. But you get the idea. It's not unique. You can express things in multiple ways. Okay, so now we're not going to see this as much with what we're going to do in this section, but when you get to Calc 2 and you look at infinite series, you'll look at alternating series where the signs alternate. So suppose we wanted to alternate. We desired a sum to alternate signs. So this is like the sum of the first 5 odd numbers, except it's not a sum. You're taking 1 minus 3 plus 5 minus 7 plus 9, and you can alternate it like that. Well, we saw that I could go from k equals 1 to 5 of 2k minus 1, and this would give me 1 plus 3 plus 5 plus 7 plus 9. Now, what could I do if I wanted these to alternate? Well, one thing is, if you take a negative 1 to the first power, that would be negative 1. If you took negative 1 to the second power, that would be positive 1. If you took negative 1 to the third power, that would be negative 1. If you took negative 1 to the fourth power, that would be positive 1. And so you see, we can get the sign of negative 1 to alternate by taking negative 1 to a power. Okay? Now, what that amounts to here is this. I'm going to add this alternating factor, this power of negative 1, to this expression. Okay? But now I'm not going to have my exponent be k, because when k is 1, negative 1 is equal to negative 1. but I want the first term to be here. I want the first term to be positive. So what I'm going to do is I'm going to do k plus 1, like that. And so then I'll have the 2k minus 1. So this is giving me these terms. This is causing them to alternate. So in other words, when k is 1, my exponent is 2, and that's positive. So I'd get this positive 1. But when k is 2, the exponent is 3, and that's negative. So I would get negative 3. When k is 4, that's 5. When k is 3, that's 4, that's positive, so I'd get a positive 5. And so it would just alternate. So this factor is a way of getting things to alternate. I call it an alternating factor. And there's two choices. You could do negative 1 to the k plus 1 or negative 1 to the k. So in other words, let's say I wanted to do this. Negative 1 plus 3 minus 5 plus 7 minus 9. So let's say I wanted it to do that. Okay, so I wanted it to alternate that way. Can you guess what I would do here? I'd have like k equals 1 to I'd have k equals 1 to 5, but then this negative 1, the exponent would just be k, and then I would have 2k minus 1. And this would give me these terms here, and then this would alternate them the way that I wanted them alternated here. So you can do all kinds of different things. You can have this exponent be like 2k, well, no, that would be all odd. Never mind, or all even. But okay, so that's how you could get sums to alternate like that, okay? Now, what I want you to do here is, in a moment I'm going to have you hit pause on the video, and I want you to go ahead and try to find these sums, and then I want you to find, oops, this should be 2. I want you to find 2 sums that give you these alternating even numbers. So come up with 2 sums that'll give you these alternating even numbers. Okay? Go ahead, press pause. When you're done, start it up again, and then you can see how you did on these. Okay. So let's go ahead and figure these out. So this is my formula. I want k to go from 1 to 3. So my first one, I'm going to put in 1 minus 1 over 1. Oops. Over 1. And then this would be 2 minus 1 over 2. This would be 3 minus 1 over 3. And so you can see that this is like 0 plus 1/2 plus 1/3. And so then you can add these together. Common denominator, this would be like 3/6 plus 2/3. Oh, plus, I'm sorry, 1 plus 2/6. Sorry, plus 2/6. And so I would get 5/6 for this one. Okay. So, what about this here? Okay, so this is causing them to alternate, and I'm going to start with a negative, right? So this would be like a negative cosine, and then when k is 1, this would just be pi. Okay, and then this would make it positive, and then I would get cosine, and when k is 2, I would get 2 pi. And then I would get a negative, because the terms are alternating, cosine, this would be 3 pi, and so on. So these I can figure out. Cosine of pi is -1, right? So this is minus a -1 plus a positive 1. Cosine of 2 pi, that's a positive 1, minus cosine of 3 pi is -1. It would look like that. And so this would be 1 plus 1 plus 1, which is 3. Okay, so that actually is 3. Okay, so now this one wants me to do k equals 2 to 5 for the expression is for the terms are 3k minus 5. So just some other formula. So it's not going to necessarily give me odd numbers. Okay, so this would be 3 times 2 minus 5 plus 3 times 3 minus 5 plus 3 times 4 minus 5 plus 3 times 5 minus 5. Okay, so this would be 6 minus 5 is 1. This is 9 minus 5 is 4. And then this is 12 minus 5 is 7. 15 minus 5 is 10. So I'm actually going up by 3's each time. Okay, which makes sense because this is a linear function with a slope of 3. So this would be 15 and 7, 22. So you should get 22 for that. Okay, now you may have been confused by this at first, and the reason is because there is no k in this formula. Okay, this is a constant, and so basically you're going to have these 4 terms, and they're all going to be pi over 2. So for the first term, putting 1 in here, you just have a constant. It's pi over 2. The second term is pi over 2. The third term is pi over 2. The fourth term is pi over 2. So you got 4 of these, which is 2 pi. Okay, so when it's a constant here, it's just you'll still have this number of terms, but the thing won't change. Okay, and you're just adding the same term up over and over again. Okay, so did you find 2 sums that give you this? Well, first of all, notice if I had k equals 1 to 4, and this was 2k, then I would have like 2 times 1 plus 2 times 2 plus 3 times 2 plus 4 times 2. Okay, and this would give me 2 plus 4 plus 6 plus 8. Okay, so one sum, I want it to alternate here, but I want the first term to be positive. So I could do k equals 1 to 4 of negative 1, and this would have to be k plus 1, and then I could have 2k. So that would be one possible sum, and there's a whole bunch of other ones by shifting these, and you could do k equals 0 to 3, and this would be negative 1, and I'm going to have to change this now because when I put in 0, that'll make this positive, so this will just be a k, and then when I put in 1, it'll be negative. Okay, and I want the second term to be negative, and so on. So I need it to alternate like that, and then when I put in 0, I got to get 2. Okay, so what I can do here is have 2, and then instead of k, I'm going to have k plus 1, like this, in parentheses. Or if I distribute the 2 over, that would be 2k plus 2. But if I have it like this, so if I put in 0, I get 1, and that'll give me 2, and that'll make it positive when I put in 0 there. So I'll get the positive 2. When I put in 1, I would get 2 here. That would give me 4. That would make it negative, so on. Okay, so this would be another way of expressing it. And of course, these answers could have varied as long as this expression would give you this alternating sum here. Okay, very good. This is a good introduction to the sigma notation. So now in the next video, we're going to learn some rules for manipulating it, kind of like some algebra rules for the sigma notation. So